So, cube root of -8, remember when we're dealing with odd roots, negative numbers are okay. And that's again because of -2 times itself 3 times is -8. -2 times -2 times -2 gets us to -8. Then the 81, or square root of 81x to the fourth. Remember we just simplified these each separately. So that gives us square root of 81 is 9. Hopefully we're not looking to factor that out. If you do, that's okay. It should get you to 9 regardless. And then the square root of x to the fourth. Remember, we're basically just end up dividing the exponent by whatever root we're taking. So 4 divided by 2 gives me x squared. Because we're dealing with an even root, we should have the absolute value on our radar. In this case, they're not necessary because x squared is positive no matter what. So the absolute values there are just redundant. Okay, they're doing the same thing as what the squarings does, at least in terms of keeping that value positive. I would accept either answer there. Okay, absolute value or no absolute value, both okay. Right, and that third one with fourth roots, we're just dividing all those exponents by 4. That gives me x squared and y cubed. Again, since we're dealing with even roots, I should have absolute value on my radar. So one way you could write this is the absolute value of x squared times y cubed. Technically, the only thing that absolutely needs the absolute value, excuse me, the only thing that absolutely needs the absolute value brackets is that y cubed, because we can get negative values with that. The x squared, you're not going to get any absolute or any negatives no matter what. Okay, so only need absolute value around the y cubed. All right, and then the last one with the cube root there, 12 divided by 3 gives me a to the fourth. 15 divided by 3 gives me b to the fifth. No absolute values needed because we're dealing with odd roots there. All right, well, any questions with how I got any of those simplified expressions? Okay. Well, we're going to get more practice with this today, as we are basically doing the exact same thing. We're just starting with some of these roots or these radical expressions either being multiplied and or divided. The other thing that I threw on here are just some vocab here. So this whole section we're calling radicals. Radicals are whenever we have this like square root symbol, but right, it's not always square root. It could be third root, fourth root, etc. So that is just called the radical sign. You'll often hear the root that we're taking, so square root, third root, fourth root, referred to as the index. And then whatever we're taking the root of is considered or called the radicand. I'm not going to ever ask you to know that vocab, okay, but it just can be helpful, especially when we're having conversations about these terms. So figured I'd kind of throw that on there for us. So when we're multiplying radical expressions, we've basically been doing that, right? When we've taken a radical expression and I said, hey, let's simplify each of those terms separately, we end up multiplying those expressions, okay? And when I multiply them together, it gets me right back to where I started. So when we're multiplying all these, as long as the index or the root that we're taking is the same, we can multiply everything together and just make this one expression. So for all of these, the first thing that I would do is I'm going to multiply what's underneath the radical symbol. So for this first one, -4 times 2 is -8. So really, we're trying to simplify the cube root of -8. And hey, we just did that. That's -2. Okay, with the next one, same idea. I'm going to multiply the number part together. So 72 times 10. So we're going to have to simplify the square root of 720. X cubed times x is x to the fourth. And then y squared times y cubed is y to the fifth. Okay, adding those exponents. After we've multiplied these together, now we'll go ahead and simplify each of them separately. So it's like, hey, multiply them together, right, as one expression, but now we're going to basically break them up again and get more multiplication going on. The only reason that I'm saying multiply them together to begin with, because otherwise you've got 6 things that you're having to simplify if you don't multiply them together, as opposed to just simply 3. Okay, so I'm going to figure out square root of 720. We'll multiply that by whatever the square root of x to the fourth is, and we'll multiply that by whatever the square root of y to the fifth is. So let's do this 720 here. That's a when those numbers get bigger, Finding the largest perfect square can be a little tricky, so this might be a good time for us to review what happens if we don't find the largest perfect square, perfect cube, or whatever root we might be working with. Right away, one thing that I know is divisible by 720 is 36. So I'm going to divide that out, and I'm going to factor 720 to be 36 and 20. So this is root 36 times the square root of 20. I picked that 36 because the square root of 36 is 6. The square root of 20, I have to ask myself, are there any perfect squares that still divide that 20? And there is. Right? I can factor 20 to be root 4, which is a perfect square, times root 5. So this gives me root 4 is 2. So 2 times 6, root 5. So this is really 12 times the square root of 5. Is what square root of 720 gets. So really what this tells me, and I think this is a really good thing to pick up on whenever we don't get this largest perfect square, is by me getting a 12 as this coefficient after simplifying, that means that whatever this value, whatever 12 squared is, likely divided 720. Not likely, it definitely divides 720. Okay, so really what I could have done here to make this a little bit quicker, 12 squared is 144. I could have taken 720 and divided it by 144. Okay, to where I get that root 144 times root 5. Root 144 is 12. So if you don't get the largest perfect square, that's okay. But again, make sure you're keeping the square root around that term until you finally take the root of it. All right, then square root of x to the fourth. We saw this last time. We saw it in the opener. That is just x squared. Again, we'll put absolute value brackets around it just so we have it on our radar. Not 100% necessary because x squared is positive no matter what. Y to the fifth is not divisible by 2 right now. So I need to factor this y to the fifth. And I'm going to factor it so it's the square root of y to the fourth times the square root of y. Where the square root of y to the fourth is y squared. And root y, we can't factor that down any further. Okay, so root y to the fifth simplifies to be, again, I'll be consistent here, absolute value y squared times root y. So multiplying all of these together, we get 12. Then I'll do my absolute value terms next. So 12 and absolute value of x squared y squared times the square root of 5y. Even better is that we recognize that the absolute values actually don't matter here because x squared and y squared is positive no matter what. So saying 12x squared y squared times the square root of 5y. Don't 100% need the absolute value brackets there. All right, why don't you all try that third one? Again, multiply them all together. If you want to simplify each separately and multiply at the end, that's fine. It's going to get there's a lot more work to do that way. So multiply them together, split it up, see what you come up with. See how we did here. All right, so starting with multiplying everything together, we're really simplifying the square root of 1,575 times x to the 6th times y to the 7th. Again, we're going to deal with the simplifying of each of these terms separately. One thing I'm recognizing is this 1,575. With it ending with that 75, I right away was like, oh, that's divisible by 25. So that's just where my head went to. Okay, I'm going to divide it by 25. 25 times 63 is that square root, or is 1,575. The whole point of picking 25 is that the square root of it is just 5. Root 63 can continue to be simplified as you can factor it to be root 9 times root 7, where the square root of 9 is 3. Multiplying all that together gives us 15 root 7. So again, what that means here is we really could have factored out whatever 15 squared is right from the start. 15 squared being 225, so I could have taken 1575 divided by 225 to get that root 7 to show up just in one step. You know, when those numbers get fairly large, more than likely we're going to have to simplify in a couple steps, sometimes maybe even 3. All right, then square root of x to the 6th simplifies to be x cubed. You 100% need absolute value brackets there. It's not a redundancy. They are needed because absolute value of x cubed, or excuse me, x cubed can be negative. Okay, so the absolute value is what allows it or keeps that staying positive. Same thing is true with the square root of y to the 7th. You have to factor it to be y to the 6th times y. Square root of y to the 6th is y cubed. 100% need the absolute value brackets there because that ends up being negative, or it can be negative. So combining everything together, we get 15 times the absolute value of x cubed times y cubed times the square root of 7y. Okay. Questions here? All right, now let's just look at division, where we're going to do the exact same thing as what we did before. I want to show us just a couple things as well here. So when we're square rooting, and when you see like a square root or any type of root happening to the numerator and denominator, you can, and really what's going on is we're just taking the square root of that whole thing all in one. So it's 18x to the 5th divided by 2x cubed. So what I would recommend is let's simplify the rational expression, okay, or the part underneath the square root first, and then we'll deal with the simplification of that square root part last. 18 divided by 2 is 9. So really we're simplifying the square root of 9. X to the 5th divided by x cubed. If I subtract those exponents, that gives me x squared. So really, I'm simplifying the square root of 9x squared here. And that works out really nice. It works out nice because when we break this down, we get root 9 times root x squared, where root 9 is 3. And root x squared is just x. But that x 100% needs absolute value brackets because we're dealing with an even root and because x can take on a negative value. So in total, this entire expression simplifies to be 3 times the absolute value of x. All right, why don't you all try the next 2? And as always, I don't need them to be perfect. Need you to try. We've got one last idea we'll talk about on the back before we're done with the notes here. Do your best. See what you come up with these next 2. All right, so let's start with our cube root here. And you don't need to necessarily show that we're taking the cube root of just that entire rational expression. If you want to go ahead and start simplifying the rational part, that's fine with me. So 162 divided by 3 is 54. Y to the 5th divided by y squared is y cubed. So really we're trying to simplify the cube root of 54 times y cubed. Cube root of 54, we have to look for perfect cube that divides 54. Be careful with, once we aren't working with square roots anymore, we might need to list out all the perfect cubes. So writing out on your paper, what is 2 cubed? What is 3 cubed? 4 cubed, etc. 3 cubed is 27, so that's why I'm factoring out the 27. That gives me cube root of 27 times the cube root of 2, where the cube root of 27 is just 3. And then the cube root of 2, nothing more that we can do there. So we get 3 cube root of 2, and then third root of y cubed. That just gives us y. We do not need absolute value brackets here because there's no, it's an odd root. Odd roots, negative numbers are okay. So absolutely do not need the absolute value brackets. All right, and the last one works out a little bit nicer because 50 divided by 2 is 25, which is a perfect square. X to the 6th divided by x to the 4th is x squared. Also a perfect square, but this time you do need the absolute value brackets because x can be a negative value. And with the square root, that's when we should have this on our radar. Okay, questions here? All right, go and flip this page over. Y'all remember when we were doing Math Excel first semester? The online homework stuff? Remember Math Excel? Some of us, we weren't huge fans of it. That's why I started to just print everything off for us. I don't know what your teachers are going to ask you to do next year for those of you that are moving on to pre-calc. My understanding is they have been using Math Excel. Actually, I have no idea if they have or not. Regardless, this next part is really important for when you're trying to enter in answers that need to be completely simplified. And it does fall into exactly what we're working on in simplifying these rational expressions. This is something that if we are not paying attention, you're not going to magically figure this out. Okay, so just a few more things, and then we'll get plenty of time to work in here. But do need your full attention here because this not hard, but we need to kind of have an idea of how this works out. So another way to simplify a radical expression is to rationalize the denominator. This essentially means to get rid of the radical term in the bottom of the fraction. This always needs to happen for a term to be considered simplified. So, right, if I have 1 divided by root 2, I can't use the property that we just talked about because that one's, well, I guess it is kind of being square rooted. But basically, if we're not taking the square root of the numerator and we can't simplify this, one thing that we can do is we can multiply to get rid of the square root term in the denominator. And just like when we're adding fractions, we need to multiply it by something that doesn't change the value of it. So whatever we multiply by here, okay, that's supposed to be saying 1 there. So multiplying by 1 won't change the value. So I'm going to multiply this by just whatever I see in my denominator. I'm just going to multiply it by root 2 over root 2. That's me multiplying by 1 because that's root 2 divided by itself. Multiplying the fractions makes this root 2. And in the denominator, that's root 2 times root 2, which is root 4. Well, that simplifies really nicely because the square root of 4 is 2. So really, 1 over the square root of 2, it simplifies to be the square root of 2 divided by 2. Another way that you can write this is 1/2 times root 2. Okay, those mean the exact same thing. Okay, so let's look at this next one here. Again, if I took the square root of everything, we're still left with a rational expression, right? There's no way for us to get rid of the denominator here with that square root in the denominator. So I'm like, okay, since I can't get rid of it by just simplifying the rational expression, I'm going to multiply it by some form of 1. I'm going to always just multiply it by whatever I see in the denominator. So root 8x, root 8x. And the whole reason we're doing this is that I'm getting 8 times 8, which is 8 squared. Square root and the squaring cancel. X times x is x squared. Again, the squaring and the square root cancel each other. So now this leaves us with the numerator being 5 times 8, that's root 40, and we still have the x. The denominator is the square root. 8 times 8 is 64. X times x is x squared. And we have to simplify each of these separately now. Let's take care of the denominator first. Root 40x we have in our numerator still. And the denominator, root 64 times x squared, simplifies to be 8. Absolute value of x. And then the numerator is not considered simplified yet. Okay, so there's actually a little bit more work that we have to do here. I'm going to recommend that we work on simplifying this on the side. I call this doing some side math. So let's see if we can't figure out what root 40x simplifies to be. Root 40 times root x. Root 40, let's see what's the largest perfect square. Is it just 4? 16 won't work. 25 won't work. So yeah, I think it has to be 4. So root 4 times root 10, or root 4 is 2. Root 10, there's nothing more that we can do. The root x, there's nothing more that we can do. So now, instead of root 40x, This is 2 times the square root of 10x all over 8 absolute value of x. Is this simplified now? There's one more thing we can do here. Back to a previous unit. 2 8s. 2 divided by 8. What can I do with that? What does that equal to? Huh? 1/4. Yeah. Okay, the 2 and the 8. This is more like dividing rational expressions. That reduces down to 1/4. So for this to be considered simplified, we do need to reduce that down as well. So this is reviewing, heck, a lot of different things we've done this semester. So that's root 10x over 4 absolute value of x. There's a lot going on there. Okay, not the simplest thing by any means. Okay, but everything that we have seen this semester. Okay, let's do this third one together because there's a lot more going on here, and there's actually a couple ways of how we could simplify this. One thing that I'm noticing is I might be able to simplify some of the variables. I don't know I'm just trying to think of what's the most efficient here. You know, let's just keep it consistent. Let's do the exact same thing we just did. Let's multiply by root 2x squared y cubed over root 2x squared y cubed. I want you to actually see what you come up with there. Probably going to get pretty messy here. Do your best. Again, it does not need to be perfect, but see what you can come up with. I'll work it out as well, and we'll check it. And we got one last thing. All right, for everyone watching the video, I got a little kind of mixed up here with pausing the recording. And give me just a sec, please. Pausing the recording and then needing to record. So if I'm saying this over again, I apologize. You can fast forward through this part. So with the last one that we are dealing with, rationalizing the denominator by multiplying just by that denominator, there's a lot of simplifying that needs to be done here. After multiplying the numerators, I get the square root of 10, x to the 6th, y to the 4th. The denominator, 2 times 2 is 4, x squared is x to the 4th, y cubed times y cubed is y to the 6th. So then I'm like, okay, I can simplify the denominator by taking the square root of taking absolute values are needed there because y cubed can take on a negative value when really we need it to stay positive. So the numerator I then simplified below here, so that's kind of like my side math of simplifying the square root of 10x to the 6th, y to the 4th. Root 10, nothing more I can do there. Square root of x to the 6th, that just ends up being x cubed. Again, absolute values are needed because it's an even root. X cubed can be negative. We want to keep it positive though. Y to the 4th is y squared. You don't 100% need absolute value brackets, but I'm just throwing it on there to be consistent. So with this side math, the numerator is now root 10 times the absolute value of x cubed y squared. From this, there's some more simplifying that can be done. And I'm kind of ignoring the absolute values here, but x cubed divided by x squared, I can divide those out. X cubed divided by x squared is x. I am keeping that absolute value around it because it can still take on, well, x can be negative, but we want it to stay positive, so it's the absolute value of x. Same idea with y squared divided by y cubed. That ends up being 1 over y. I am using absolute value brackets there because of it can take on a negative value. There's a lot going on here, a lot of simplifying. These are good practice. I don't expect this to be an assessment type problem though. All right, and then again, I think I didn't get this in the video the first time. If I did explain this already, feel free to fast forward. Last kind of thing we're going to work on simplifying here is where we need to use a radical expressions conjugate. We dealt with conjugates back in Unit 5, where basically a conjugate is where we have a binomial expression, so 2 terms, and the conjugate is where we just switch the sign on the square root part. So the conjugate of 2 minus root 3 is 2 plus root 3. And the whole reason why we use conjugates is because when we multiply those together, we're going to get the square root terms to go away. Now, just like before, I need to multiply this by 1. So I'm multiplying by 2 plus root 3 over 2 plus root 3, which is 1. Then I'm doing some multiplying, some foiling. So 2 times 2 plus root 3 is 4 plus 2 square roots of 3. And the denominator, I'm going to FOIL this. 2 times 2 is 4. 2 times root 3 is positive 2 root 3. And then negative root 3 times 2 is negative 2 root 3. The last term, and this is where when we had talked about conjugates before, a lot of us kind of got this part mixed up. I have a negative root 3 times a positive root 3. So the negative times a positive is negative. Root 3 times root 3 is root 9, where root 9 is 3. So really the denominator, after the positive 2 root 3 and negative 2 root 3 cancel, is 4 minus 3, which is 1. So this whole expression simplifies to be 4 plus 2 times the square root of 3. All right, last one. We kind of did the same thing here. So multiplied by the conjugate of the denominator. Again, what's telling us that we need to do that is that this is a binomial expression. Binomial meaning 2 terms. So multiply by 3 plus square root of 2x, both in the numerator and denominator. That way we're multiplying by 1. This x will distribute. In the denominator, that FOILs out. So that makes the numerator 3x plus x times the square root of 2x. In the denominator, we get 3 times square root of 2x to cancel out with the negative 3 root 2x. And then I have this negative root 4x squared, where that simplifies to be 2 absolute value of x. Root 4 is 2, square root of x squared is absolute value of x. Nothing more that we can simplify here. All right, everyone else is working on this last problem, so go ahead and pause that video, work through it, and then we'll check it. Some of the others we've seen here. So, again, the conjugate that we're going to multiply by is x plus root 5. Again, that needs to be x plus root 5 over x plus root 5. That way we're multiplying by 1. In the numerator, we have y times that x plus root 5. I do distribute that y, so that makes that xy plus y root 5. The denominator, so multiplying the conjugates, that needs FOILed. X times x is x squared. X times positive root 5 is x root 5. Negative x, or x times negative root 5 is negative x root 5. And then negative root 5 times positive root 5 is negative root 25. Negative root 25 is negative 5. And again, we should always get those square root terms to cancel out. So that makes the denominator x squared minus 5. So this simplifies to be xy plus y root 5 all over x squared minus 5. Okay,